Okay, I think we can start. So good morning to everyone, and thank you for assisting to this workshop, especially in this date at the end of July. We are very glad to see you all connected and to participate into this very interesting webinar in the framework of the Level Up project. This workshop will be focused on protocols for remanufacturing and upgrading high-value metal components, and is a part of the dissemination activities in the framework of the Level Up project. My name is Diego Espina. I'm a senior consultant at Innovali Association, which is one of the partners of the project, and a representative of the Digital Factory Alliance, which is hosting this event. Just a quick reminder, the aim of the Level Up project is to offer a scalable platform covering the overall life cycle, ranging from the digital twin setups, the modernization actions to diagnose and predict the operation of physical assets, to the refurbishment and manufacturing activities toward the end of life. In situ repair technologies and the redesign for new upgraded components will be facilitated through virtual simulation for increased performance and lifetime. Today's workshop, as I said before, is supported by the Digital Factory Alliance, which is an initiative to support the digital transformation of the manufacturing sector. You can visit the webpage of the Digital Factory Alliance at digitalfactoryalliance.eu. So basically, the DFA is a vehicle to support the dissemination and exploitation of project activities. And you can find over there a space for anyone in the manufacturing community. If you are technology provider, if you are an end user, if you are a digital innovation hub or a technology and testing facilities, there is a way for you to participate into the DFA. We have a lot of catalogs for innovation when you can showcase your products, and as well as different vehicles of dissemination, newsletters, and webinars that you can also participate and can include into your dissemination activities in your project. So I encourage you to visit the webpage, and if you have any question, just let me know. So without any more hesitation, I will share the agenda today. 1 second, share my screen. So can you see my screen now?
Yes.
Okay. So the agenda for today is what you're seeing in the screen. We'll have the AM approach, and it's going to be delivered by Sara Carracelas from IMEN, following by a scanning of technologies for remanufacturing. Then we'll have a presentation, CAAP for remanufacturing and upgrade from Thinking Additive in charge of Marco Sharvik. And again, AIM simulation by Mustafa Megad from ESI, okay? And then we will cover up the different Level Up AM use cases, but different participants of the project, okay? So without no more hesitation, I will give the floor to Sara, so she can start with the AM approach. Sara, the floor is yours.
Okay, thank you, Diego, for the presentation. I'm going to share my screen. Okay, suppose that you are seeing. Well, my name is Sara Carracelas. I am an engineer with a major in mechanical engineering. I work in IMEN in the field of advanced manufacturing with laser, mostly with additive manufacturing. The idea of this workshop is to give an approach to the additive manufacturing technologies applied within the Level Up project, and an idea about the digital thread followed to apply the processes. Okay. The idea to make it easier to approach is to give a brief summary about additive manufacturing, the two additive manufacturing technologies applied here, and present a schema of the digital thread followed. After presents the use cases developed inside Level Up, a year with broken seeds to manufacturing in Estampaciones Mayo, The manufacturing of a new heated die belonging to a pultrusion line in Jerez, our reading of a coordinate measuring machine in Trimec, extrusion light in isocon with wear, and also our bed cover belonging to the vertical lathe in Rosulink. For SLM application, two upgraded components, a pinion for magnesia and a cooling nozzle in Chile. Okay, additive manufacturing. The definition of additive manufacturing itself is manufacturing using CAD software to deposit material layer by layer in a precise way, generating a near net safe part. For everyone, the most widely known additive manufacturing technique is the plastic extrusion, or FFF, technology developed during years and now accessible to everyone. All of you probably have one of these machines close, maybe at work or maybe at home. As nowadays, both commercial machines and the consumables are really affordable. Additive manufacturing, compared to conventional manufacturing techniques such as machining, offers advantages like the reduction of waste during manufacturing, and additive manufacturing generates in parts nearness safe and also functionalities like the possibility to manufacture in multi-materials and in complex structures. But despite the fact that outside the industry only this additive manufacturing technology is commonly known, the FFF extrusion, the range of technologies commercially available and under development is really wide, as you can see here. Here you can see one of these schemas that shows a range of technology classified considering energy source used for the process, the sequence of manufacturing, and the type of feedstock. Inside Level Up project, we apply two different techniques that employ laser as energy source, the two with the red boxes. But they have different feedstock materials and also different methods of manufacturing. Powder bed fusion, in particular SLM, and laser direct energy deposition, also called laser metal deposition, with powder and wire as feedstock. Here we have mapped the difference between the techniques. Selective laser melting brings low roughness and high complexity of shape with low deformation in comparison with the other techniques. But also the deposition rates are lower. By contrast, direct energy deposition has higher deposition rates, but limiting the complexity and increasing the roughness and deformation. For that reason, it's usually to choose SLM for small parts that require higher complexity in geometry, and for bigger parts, the direct energy deposition. Selective laser melting consists on an enclosed machine with a powder bed, a laser scanner with a detectable lens melts material into complex shapes, and when passing between layers, a plunger plunges the part down, and the machine applies a new layer on top of the previous, melts a new layer of material. Also, these closed chambers also make it easier to work with inert atmospheres and more reactive materials like titanium, aluminum. On the other hand, direct energy deposition melts both materials, powder and wire material, which is directed to the area where the energy source, in our case laser, interact with the substrate of base material, which can be part of the piece or removed later. For powder cases, a nozzle is placed just below the laser head that focuses the laser. This nozzle concentrates a jet of powder on the place that laser interacts with the base materials, melting the powder on this substrate. To generate shapes, a motion system such as a robotic arm or a CNC system is needed to move the laser head and the nozzle assembly, and deposits wells in a similar way as in the case of plastic extrusion, FFF. After generating a layer, the motion system moves up the layer height in theta coordinate and deposits the next geometry, the next layer. Here you can see two different types of nozzle, the coaxial ones that focus the jet powder in a point, and the multi-jet powder. The other way to supply material to the direct energy deposition process is in wire form, a material widely used in arc welding, which make it easily accessible, as well as facilitating the construction of an additive manufacturing cell due to the reuse of equipment such as arc machines present in almost any company of metal mechanical sector. Here too, there are different ways of feeding wire, literally using arc welding tools, as I commented before, or coaxially with more precise manufacturing, but that also needs more expensive laser heads. Also, the direction of manufacturing affects the result. Laser leading is the direction in which laser goes before the wire, brings more jointed welds or tracks, but this process can be done with hard wires like steel. For the harder wires, laser trailer, in which the wire goes before laser, is the optimal technique. And for that manufacturing, the thread that this process follows start with pre-scanning to achieve the dimensions of the part to remanufacture, or with a 3D file for a new component to upgrade. Having the materials and the requirements, a batch of trials is carried out to achieve the most suitable parameters. With these parameters, we obtain the width of the track to manufacture a layer with the proper overlap between tracks and to have the height of the layers, because we need to move to the next step, that is the generation of the path planning. With both, a simulation is performed. The results, if they are favorable, it's possible to generate the trajectories in a different way, giving to the part a different cooling speed. That loop maybe is necessary to do it multiple times. When the results of the simulation are acceptable, the part is manufactured, and after that maybe it's needed to machine it or to apply a thermal treatment of stress release. The last step is to scan again the part to confirm that the final dimensions are achieved. And now, moving to the first step of that thread, we can start from a CAD file if we are going to start the part from zero, or if we are going to repair or remanufacture, start from an existing part. And in that case, we need to know the dimensions of the base part to generate the path planning. So for that, we applied a scanning process. The scanning technologies most widely used depends on the technique used. Maybe it's contact-based, photogrammetry, laser triangulation, structured light, or time of flight. Also, the mobility of the equipment define the technique. It can be handheld, stationary, or automated with a robotic arm. And inside the project, inside Level Up, mostly two different equipments were used, the handheld and an stationary. You can see. On the next slides, it's possible to see the results of the scanning process applied during the project, the pre-scanning before the manufacturing, because we applied another one of the final of the process. Here, the scanning process at itself and also the post-processing to achieve the last part of the year can be seen. As I commented before, maybe a post-machining is needed. Here is, you can see the pre-machining tools and the post-machining part. And also for trim use case, the surface worn can be seen here, and also the magnitude that is really low. Nesh also applied a scanning process to the tooling bed cover to achieve the magnitude of the wear. And the same for the isocon die. After the manufacturing of the upgraded luxury nozzle, KNWE applied a scanning process to find the possibility of distortion generated during the selective laser melting manufacturing. And now, moving to the path planning step, Marco from 3D Additive is going to present the development of that field.
Thank you, Sarah. Let me just share my screen. I assume you can all see it, unless let me know. Otherwise, let me know. Hi everyone. My name is Marco Chorbek, and I represent Thinking Additive from London, UK, who is one of the partners in the Level Up project. And we were tasked with basically designing and developing computer-aided process planning tool for remanufacturing and upgrading of high-value metal components. The agenda regarding the process planning tool is basically just divided into two halves. We thought that it would be a good idea to talk about slicing features and toolpath features that distinguish such a tool from just a regular slicer. Slicing features are just a group of algorithms that allow us to go from volumetric geometry to surfaces that identify the layers where we need to deposit material. And then toolpath features, on the other hand, would use these layers in order to develop trajectories. Now, starting from the slicing features, in the Level Up project, we are trying to implement this new interesting concept which we called selective slicing concept. Basically, as opposed to just slicing the entire part as it is usually done in kind of standard additive manufacturing approaches, we enabled the selective slicing by providing a closed volume that you see here in gray, and the slicing surface that you can see here depicted in green. So basically combining both of them, we are able to slice just a portion of the part instead of the entirety of the object. This is because if we would like to go ahead and apply remanufacturing and upgrade, it would probably be done only on a portion of the part or on top of an existing object already. Of course, this is a cumulative process, so there's nothing blocking us to apply it several times. As a matter of fact, we can apply it as many times as we need according to the application, or until we've exhausted the entire volume of the part. Now, how does this translate into a real application? Let's assume that we have this gray CAD model here of a metal part. This would be just a corner that we would like to either repair or upgrade. And let's say that this is the volume that has been already removed by machining, and now we want to deposit it again so that we achieve repairing or upgrade of that portion. Using the selective slicing concept, we can use the bottom surface as a slicing surface to develop these two groups of layers, basically the yellow one and the green one that follow the left and the right wall. But this is just one option that can be done. Actually, if we use a different order into setting up this selective slicing concept, we reach a different kind of process setup here in the corner. Now, this, of course, has limited implications only in that area there, but from our experience, process experts and final users appreciate highly the possibility to be able to control exactly what is going on in every kind of portion of the process execution. So this gives different process parameters and process flow, basically, and gives a complete freedom to guarantee part quality in the end. And it's not just the order that we are able to change. We are able to also provide slicing in a completely different layout. So here you can see an example where the slicing surfaces are actually the walls of the CAD model itself. So this leads to an entirely different process where instead of, for example, in the previous case, if we were to go and deposit from the bottom upwards, here in these cases, for example, considering the left wall, if we start with that one, we start from the left and then deposit the entire layer close to the wall and then move to the right. Now I'm going into detail into these aspects also to provide the reasons why we have referred to such a tool as a computer-aided process planning tool, as opposed to just a regular slicer. So we think that in this case, there are many more variables and process parameters that need to be controlled. And so it really becomes a tool that enables the final user to have a detailed control over the process flow, basically in all of its aspects. This also represents our daily struggles in thinking additive as a software development company, to understand how much process freedom we want and how much of this process freedom we would like to offer to the final user, which usually goes contrary to the automation. So the more parameters and the more options that we apply to the tool, then it becomes a bit more difficult to use and complicated to use. Whereas if we push for the automation part, then we lose a little bit on the process quality and guidance. Talking about the slicing features, there is another feature that I would like to talk about, which is slicing of non-planar layers. So because of the reason that parts in industry are not just made from flat surfaces, there's usually the case where we need to remanufacture or upgrade a part that has curved surfaces. So in this situation here, you see a part with a single curvature surface, and here the red surface has been used as a slicing surface to propagate it inward and develop these 3 layers that can be used for remanufacturing or upgrade of that particular part. Again, this is a relatively simple case for a single curvature geometry. This could easily get much more complicated if we go to the generic case. So, of course, surfaces can span into doubly curved surfaces in space. And, of course, a combination of different orientation for slicing can be used. So this gets particularly attractive and interesting in the cases of upgrade, where maybe we would not like to use an expensive material for all of the volume, but we can use a cheaper material, let's say, to deposit the bulk of it, and then just use the high quality, resistant, or hard material just for where we need. Let's say this could be a material with high hardness or particular chemical resistance, for example, if it's necessary. Then moving towards the toolpath features, which is the second group that I mentioned earlier. Of course, a tool like that would need to develop the toolpaths for applying additive manufacturing technology. In this case, this CAAP tool, we see it as a kind of a single point process planning tool. So it goes well with the direct energy deposition techniques. And of course, the first feature, for example, that would need to be done is be able to develop these toolpath trajectories, but not only in a planar sense, but also in spatial cases where we have curved layers. And whenever we go into toolpath generation into 3D space as opposed to 2D surfaces, things get substantially more difficult mathematically. And of course, it's not just a matter of depositing the or generating the toolpaths, which you see here in gray, but they need to be incorporated into a chain of kinematic chain of movement that explains the entire movement process. So here you can see in blue approach curves, in orange depart curves, and in green travel moves. Sorry, I don't know if this is blocking your view. The second feature that I would like to talk about is that we've also noticed in the thinking additive in the level up project is the need to do tool orientation control. I'm not aware. Okay, there we go. Basically, because of the fact that we need to sort of dance around an existing part or a substrate, this problem of collision avoidance becomes much more present and difficult to manage. So thanks to Inegi, here we were able to simulate some of the toolpaths, and in the beginning we noticed that there was a real danger of physical contact between the toolpath head. This is a powder-based DED process. And of course, process planning tool that we are designing would need to have a way to control the tool orientation. And in this case, we just applied a limiting of the orientation inside of a certain window that enables the process to be feasible on a part like this. Then the process is not done in ideal process parameters. So the tool is not perpendicular, or the inclination between the tool and the substrate is maybe more than it would be ideal for execution, but this allows at least the process to be executed as opposed to not have an option to do that. Another feature that we noticed that again touches the orientation control is give the user basically the freedom to select the orientation that they want, but not for avoiding the collisions, but for process execution. So even if geometry is missing to explain that that orientation, it's good to have basically a way that the final user can even manually select the orientation that they want. so that the process could be executed into ideal conditions. So here, what you see is a scan geometry of an existing geometry already, and the toolpaths that have been developed for the missing part. And here, the process expert has preferred the angle of, let's say, 24, 25 degrees to execute the process in a good way, so that adhesion between the filament, the deposited strands between the initial toolpaths and the existing geometry is done well. Finally, there's another feature that I would just like to briefly touch upon, is the fact that whenever we are dealing with trajectory generation in cases of remanufacturing and upgrades, we cannot permit ourselves the liberty to not look around. So basically, whenever we develop the toolpaths, we need to be aware where the existing geometry is. So for example, in this case, this distance between the starting toolpaths and the existing geometry has been closely monitored and controlled. This means that a certain pattern for one layer cannot be applied on the other layers, but each layer needs to be analyzed individually to maintain a specific distance towards the existing geometry. And this increases the part quality in the end. Finally, I'd like to show you just 30-second video that we developed some time ago. This is a mock-up of a user interface. You could see here an example of a gear with a damaged tooth. And basically, we are able to just provide a slicing surface to the model and use the selective slicing approach to develop trajectories just for the part where it is needed and it is necessary. Of course, this is a bit of an oversimplification, because a lot of the options for close process control that I spoke about earlier are not there, are not present. But we are still working on developing this user interface, again, keeping in mind that compromise that I spoke about earlier, how much we want to give to the user in terms of process freedom, and how useful and then user-friendly we would like to make the part. That's all from my side. I think it's Mustafa's time.
Yes, thank you, Marco, for the presentation. Yes, right now we move to AM simulation by Mustafa Megadet from ESI. So, Mustafa.
Yeah, I'll just share my screen. Which screen are you seeing right now?
We're still not seeing the screen. Now we're seeing your desktop.
Now you should see the presentation mode.
Now we're seeing the screen. Yes, now we see the presentation. Yes.
Okay, sorry for the delay.
No
so I'll be
problem,
talking about the simulation of repair processes. Basically, we take the preparation work done by or presented by Marco and check if the behavior will be conformal to what we actually want to do. So the motivation behind the simulations is to identify and mitigate problems prior to printing or cladding. This image here on the right-hand side shows a catastrophic failure where the material has delaminated completely off the substrate and even breaks in its own content. So this kind of failure, we definitely don't want to have it, but there are a lot of other smaller defects which could lead to performance degradation or property degradation, which we do not want. So if we can identify this prior to the printing, that would be a good thing to do. We would like to optimize the process. So the quicker we can perform the repair process, the cheaper the component, and to maintain or improve the quality of the part being repaired or remanufactured. The general challenge of additive manufacturing in general is that the material and the product are created at the same time. So we have to manage the material behavior to achieve the goals or the requirements behind the product. So these motivations make it necessary to look at different aspects of additive manufacturing and repair. Starting with the requirements, we would have a CAD model where the designer decides what he would like to do, he or she would like to do. We check the feasibility, so which process, which manufacturing route is the most suitable. Is it casting, is it welding, whatever it may be. Here in this case, we check if it's additive. If acceptable, if it's something which is feasible with this technology, then we calculate the cost. If the cost is financially acceptable, then we start optimizing the process parameters and then go to path planning as presented by Marco. Check for collisions, so kinematic modeling of the printer head. If collisions happen, we can revisit the path planning. Potentially, the further you go backwards, the more expensive the optimization process, but usually this loop would be sufficient. Once you have a suitable path planning, you can look into the thermal modeling of the component. This gives us cooling rates, which are very important to determine the as-processed properties. So these go back to thermodynamic-based models which can predict the properties. Usually the properties you get from data sheets are not the properties you need for the actual printing process. If you have the properties, of course, you don't need this loop. We then look at distortion. Please note that we don't do a thermomechanical modeling. That is computationally expensive. We separate the thermal model to predict properties from the distortion models to predict residual stresses and deformation. And then finally, we have comparison with the CAD model and whether it is conformal to the original designer intent. If yes, then we're done. We can continue to post-processing. If not, we can try to compensate and redesign the component so it does fit. What are the processes we support? There are, as Sarah presented, three main metal-oriented processes. Laser powder bed fusion, where you spread a powder layer, the laser processes the part, and then the table moves downwards and you put a new layer of powder. Usually it's a very quick process. As you see the lasers going back and forth, you can hardly distinguish these lines from one another. Then we have powder-based direct energy deposition, where you usually have a coaxial nozzle. The laser comes in the center, heats a focus point where the powder particles meet together, and this is where the substrate will be placed. And here we have an animation of a part being repaired by Inegi. Then finally, we have the largest process, wire arc additive manufacturing. You see the scale of parts which can be built by this process. Basically, this is more or less traditional welding, only a lot of it. As I explained through these processes, you can see that the part size increases. Powder bed fusion has the smallest part sizes, and WAM has the largest part sizes. And in the other direction, we see that the geometry complexity is highest for powder bed fusion. Here you can include conformal cooling channels, and there's a lot of details which can be included, which in larger scale models would be difficult to account for with WAM. For each of these processes, we have a different set of tools. Here's an example from the level up use cases, the Lucchini nozzle upgrade. This is the original design. It was redesigned by CAAP, where generally we use the new material to withstand wear and corrosion in a better way. Also, less material is used. We assess the cost. Then we assess the manufacturing process. Here we're looking at the distortion. The distortion was found to be fairly large, so it was compensated for. And we get a new geometry, not exactly that what was designed. It's a new geometry which has to be printed. But when it is printed, it moves, it deviates from its intended shape to achieve the shape which the designer wanted. And the deviation is below 200 micrometers, which is quite accurate, or that's what we considered for this part. And then it was printed by KMWE, 4 different designs and methods to print, and then it goes to functional assessment. An alternative process, powder-based laser metal deposition, was used for the isocon die refurbishment or repair. We see here that this die surface has a lot of wear and problems which need to be removed via milling. This green volume is the volume which was removed and is to be replaced by a new material. Now, the problem is when you mill, you move very close to the cooling channels so that this distance gets to be very critical. Critical how? It is critical in 2 senses. First is it might be too small or even non-existent so that you can't really print on top of it. And the other thing is it might be too thin to withstand the generated stresses. So we looked into different options, how to deposit material on these surfaces. The strategy is shown here. We print on one side, then the other, and then we close on the top. And here we look at the melt pool size as well as the heat affected zone. We are most interested in the dimensions so that we do not melt the remaining material away. Yeah, it has to stay there. So that we can deposit metal on it. And the second aspect we're looking into is usually the deposited layer has the highest stresses. So if the layer is very thin, like a very thin foil, you can indeed deposit on it, but it will not withstand these stresses. So we are looking at the stresses and the corresponding plastic deformation to make sure that when we deposit the material on these surfaces, it will also be of good quality and withstand these stresses. Then finally, we look at the gear of a very large application. You see the gear size as compared to the components in the background. It's a very large component with a lot of damage on certain corners, which were scanned as presented by Sarah at the beginning. The gear was cast using a gray cast iron, which has been used for several times. So we were concerned about how the material absorbed different impurities and how it will behave once we deposit new material on top of it. So we looked at deposition strategies provided by Marco, and we look at the thermal history of these repairs. So you see when the laser is far away from the actual repair line, we see a preliminary preheating. Then the laser is closer, so we have some melting, and then the laser moves on that point, and then it moves away. Based on this thermal history, we can look at the material behavior and judge whether it's going to crack or not. The crack susceptibility was predicted to be very high for this material. So instead of using a similar steel, a nickel-based alloy was used instead. There will be more details on that later on. Okay, so in summary, we have a versatile modeling platform with different modules which address different questions. We can look at the metallurgical evolution of the alloy. We look at the melt pool dimensions as well as the heat affected zone to make sure that it does work in tight parts, in small parts, thin parts. We are particularly interested in the actual temperatures and the gradients. We can look at defects. We can look at the as-built properties, which is also input for post-processing, like heat treatment. And we can predict the final component shape, and distortion compensation is performed if the shape is too far away from the original intent. Things I did not present in detail, just very, very quickly sometimes, is that the physics-based models, they do run several times to optimize a certain aspect. For example, if the melt pool is too large or if we see a lot of cracking, then we run a numerical design of experiment to see where to explore the different process windows. When we have such information, so 25, 30 simulations, we can run them through machine learning and explore the rest of the process window even quickly. So we complement the physics-based models with machine learning to get something we call the hybrid twin. And we also complement the tools available with feasibility assessment tools. So not every manufacturing route is suitable for a certain component. If there are a lot of holes, or the size, so this feasibility tool will assess these different aspects and recommend a certain way forward, as well as economic aspects are considered. So if it recommends us to use, let's say, welding, and the cost is too high, then maybe we have to go to something else. Yeah, that's it. Thank you very much. And I believe...
Thank you. Thank you, Mustafa, for the presentation. And I think we have space for one question. If anyone has a question to the speakers, just let us know. Is anyone? Okay. I think everyone has understand the information very well. That's good. Now we continue with the AM use cases. We have several of these use cases to be presented right now. The use cases will cover ESMA, IPC, and TRIMEC from IMEN, ISOCON, and Toshulin by Joao Rui, and SLM cases by Rob. Okay, so Sarah, floor is yours.
Thank you. Now we're going to enter to describe a bit the work carried out during that manufacturing step of the AM flow that we presented before. Inside Level Up, two main processes were described and applied: the remanufacturing of a component that has a lost part, or maybe wear, or the upgrade of an existing component, manufacturing it with a new design or improving functionalities or behavior. So for Estampaciones Mayo use case, the part is a big chair belonging to the kinematic chain that weighs more than 2 tons. And due to the different stresses generated during the stamping, some the laser thing. During the stamping, some cracks and breaks appeared on the teeth. The idea is to remanufacture the lost hoof using additive manufacturing. Wire was selected as feedstock for the highest deposition rate and the easiest containment of process waste because we don't want to generate a lot of waste inside the kinematic chain of the process. Unfortunately, the repair cannot be carried out on the press at the pilot line facility. So the idea was to replicate the conditions at IMEN. The setup selected were a small robot with good reach and only 50 kilograms of weight, compact laser source. The decision of this smallest laser source was because a most powerful laser needs a bigger chiller, and our idea was to make it everything portable. So we choose a small laser source, but with enough power to melt the material. And also a small wire feeder from a pistol is used to provide the wire to the process, because we only need to push the wire to the process. The assembly of the laser head was a narrow laser head with a short collimator and a large focal length, moving the focus away from the laser head and also the wrist of the robot to avoid collisions with the gear and also the structure. This gear is made of GGG70, as commented before, a cast iron with spheroidal graphite. That material is sold in wire form, so we propose it to different materials, a steel and also nickel. Both are hard and cracks appeared during the cooling. The option of the preheating system was studied, but heat the wall gear to a certain temperature is impossible because the part acts like a big sink of thermal input. So most friendly nickel alloy was used for the remanufacturing, and also this alloy gives us the possibility to add a harder material on the top, because it acts like a bond between the base and the hardest material in the surface. Those are the results of the mechanical properties tested in IMEN laboratories during the process parameter obtention. We tested micro hardness to a part manufactured with wire, also tensile strength following the ASTM E8 with subspecies of samples. And also we tested the wear using a volume disk test. Also, a structure was manufactured to hold half of the gear. As the part isn't going to be tested, we prefer to manipulate 1 ton instead of the whole gear. So the gear was located inside the structure and the robot on the top, preserving the accessibility and the distance between the robot base and the gear, like in the real scenario of the press. Here you can see some pictures of the process of the manufacturing and also the final results of the manufacturing process. Other use case was the IPCCRF pilot line. We manufactured, in IPCCRF, they manufacture plastic profiles using pultrusion process. So that was chosen to be upgraded. They wanted to improve the line, and a bigger die was designed. The proposal was to apply a coating to the surface that is in contact with the profile and becomes more damaged during the timing service. Two materials also was proposed, a cobalt alloy and a nickel. Firstly, some scaled tests were manufactured to test the manufacturability and the interaction between materials. Despite the fact that in the scaled test results of the cobalt alloy seems acceptable, when we transfer it to the large part that weighs more than 100 kilograms, and even using a preheating machine, when depositing the first layers of cobalt alloy, a lot cuts appeared and propagates through the coating. So we replaced the cobalt alloy for an inconel, and also we used a preheated system here to in 250 degrees. And also you can see the progress of the manufacturing. And here the results of the surfaces with the coatings. And the last use case that I developed was the remanufacturing of an air beading belonging to a coordinate measuring machine. The wearing the surface of the beading causes a waste of money in compressed air during the use of the machine, but replace the part is also really expensive due to the material used for the part is an alloy usually used in aeronautics. The reason of that is that it's needed to a hard material, but also light to decrease the consumption in compressed air. The process proposed was to apply a coating of material to the work surface using direct energy deposition with powder that brings a better resolution to the manufacturing. The material proposed were the same material as the beading, 70-75 aluminum alloy, and a most suitable alloy for welding, commercially known as scalmalloy. The reason of that is that 70-75 is described as non-weldable in all the materials handbook. During the previous trials, 70-75 doesn't generate defects, but when we move it to the final surface, as in IPC this case, we used a secondary beading that makes sense to us for trials. Some open pores appeared, so we moved back to the scalmalloy to deploy the remanufacturing. And here you can see the setup during the remanufacturing, some simulation of the movement of the robot, of the propellant, and also the final results here after post-machine. And that's all for my part. I'm going to
thank you.
Thank
you, Sarah.
Stop sharing.
Okay, so thank you very much for the presentation, and we now move to Joao Rui from INEGI with the use cases from Isocon and Toshulin. So Joao, the floor is yours.
Hi everyone, my name is João from INEGI. I will start by presenting you the Isocon use case and then move on to the use case for pilot line Toshulin. The agenda for this presentation will be very short. First, I will show you what was the status of the part chosen at the beginning of level up and what were the steps to be able to repair it through additive manufacturing. The part chosen for this use case was the extrusion die used by Isocon. The die is installed on Isocon's extrusion line after the extrusion cylinder and before the cooling bath. It is responsible for giving the extruded profile its final shape. The die is an assembly of several parts, many of which show significant wear from its use. Typically, the edges and the inside of the die walls are the most affected areas. The wear on the die creates quality problems in the final extruded profile. As you can see in the figure on the lower left, highlighted in dark blue, the areas of intervention of in this use case. The extrusion die appears to be suitable for repair with additive technology for several reasons. It is an expensive component with long delivery times. Big defects are difficult to repair and normally lead to die replacement. Also, the main wear occurs only on a limited area of the part. The proposed steps for the repair through additive manufacturing are to perform a 3D scan of the part to assess where material needs to be added for a successful repair, machining to create flat and consistent surfaces, and to enable us to reach the deposition area on all areas of intervention. And finally, the additive manufacturing process can be done. The process in here is direct energy deposition using powders. The first hurdle was to find a suitable material. The chosen material needs to have a high surface hardness similar to the original material, and it should have excellent corrosion resistance to be able to withstand the extrusion process. Simulations to evaluate residual stresses and the distortions on the repair part were performed, as mentioned by Mustafa earlier, as well as simulations to understand the best parameters to use when the deposition occurs very near to the cooling channels internal to the die. After this, a set of experiments was performed to validate multiple dimensions. As can be seen in the table and the figure on the right, the experimental results have very good correlations with the simulations. Following this work, a set of experiments was conducted to evaluate how the depositions would behave on a curved surface. The objective of these experiments is to understand how different strategies affect the final results and what would be the best tool paths to repair the die. Special attention was also put, as mentioned by Marco, on creating strategies to avoid the collision between the tool head and the part being worked on. Using the knowledge gathered on the previous steps, the geometry for machining can be defined. The objective here is to create a known and consistent surface and to gain access to areas that would be impossible to reach using the original geometry. The goal is to remove the least amount of material, maintaining enough thickness to the cooling channels below the surface. Having the parts machined, the next step in this repair would be to perform the deposition on the new material, machine the parts to their final dimensions, send them back to Isocon for testing and evaluation, and finally perform an assessment of the suitability of this technology in this use case. This was my presentation for the Isocon use case. I'll move on to the Toshalin pilot line. The topics are similar. Firstly, I'll present the part as it was, the additive manufacturing process, and the final assessment that was made. The part here chosen for this use case was the bed cover for the vertical lathe. The main function of the bed cover is to close the space under the table of the lathe. The part is made from GG20 gray cast iron and weighs approximately 340 kilograms. The bed cover prevents chips and coolant from entering the space under the table. This space is lubricated and houses the table bearings and gears. If this space is contaminated in any way, mechanical damage to the table drive or damage to the oil charge in the lubrication circuit can occur. The main cause of wear in this part is abrasion from chips from the machine material that causes the effectiveness of the seal to decrease. So the gap in the seal increases in size, making it lose its original shape and therefore its function. The bed cover part appears to be very suitable for repair with additive technology. It is a large part that is produced by casting, machining, and subsequent heat treatment. This makes the acquisition of a part expensive and the delivery times to be very long. Also, the main wear occurs only on a limited area of the part. So if a repair is done to the worn area, the part should be fully functional again. The proposed steps here for the repair are to machine to create a flat and consistent surface. Next, a 3D scan of the part is done to assess where material needs to be added and how much to successfully repair the part. And finally, the additive manufacturing process can be done. To aid in the definition of the additive manufacturing process, a set of simulations was performed aiming to assess residual stresses, plastic strain, the need or not to preheat the part, and the occurrence of cracking in the part after the deposition process. With the help of these simulations, several experiments were performed with the material to be used in order to obtain a set of parameters that would guarantee good mechanical performance to the repaired part. The main hurdle that was overcome here was the prevalence of cracks in the deposited material. Next, in order to obtain a good geometry of the deposited material, several toolpath strategies were studied. The main goal here was to arrive at a strategy with good results where the start and end of a deposition meet. After arriving at a good set of parameters and strategies for the deposition on the bed cover, the additive process seen in the video below was performed. After each layer was done, a visual assessment of the result was performed. Between layers, a 20-minute wait time was established in order to allow the part to cool down to room temperature, avoiding the development of cracks in the material. The deposition process overall took 22 hours to complete. After this, the part was shipped to Toshulin for assessment of the final result. The first assessment was of the part functionality. The part was measured for geometrical deviations. Based on those results, it was stated that the part after repair is fully usable without the need for further machining of the added material. The dimensions and shape of the repaired area comply with the requirements set by Toshulin. The second assessment concerns the cost and time used to repair the part. 3 basic scenarios were chosen to assess cost and time. The first is to repair using this new additive technology. The second is to repair it in a standard way, usually done with replacement of the worn area with machine segments. And lastly, the production of a whole new part. The results show that repairing this part with additive manufacturing takes about as long as the standard repair method. However, the costs involved are significantly lower, and since this was the first repair done in these conditions, it is believed that improvements can still be done to lower costs even further. Thank you. That was all from my side.
Thank you very much, Joao, for the presentation. Now let's move to the last cases to be presented by Rob van Loon. There are the SLM use cases in leukemia and malignant. Rob, the floor is yours.
Yeah, if Joao can stop sharing his screen, then I can share mine.
Yeah, trying. Okay.
Yeah, perfect.
Okay.
And let's bring it up. Let's put it on the slideshow.
Okay.
So
Okay.
yeah, first a short introduction. I'm Rob van Loon. I work as an additive manufacturing engineer at KMWE. And the technique we employ here at KMWE is called selective laser melting. It's a little bit different than the technologies you saw in the previous 5 use cases, where mostly directed energy deposition is used. Selective laser melting is a little bit more small scale, where we apply a thin layer of metal powder and we locally melt it to create basically almost any shape possible. All that is required for this technology and the basis is a digital CAD model. And from then on, we can start producing parts. All is to say, again, which you can design, we can actually produce with this way. The main advantages, and that's also shining in the two use cases I have in store, is that's a flexible technology. And it means that you don't have any upfront investments in big molding or fixturing to create a large amount of parts. And also any part can be unique. So it specifically shines at the locations where you only need a couple of components or even just one to upgrade a specific machine for making a specific part or to create spare parts in a quickly fashion. So if we're looking towards the two use cases that I have in store, first off is use case from Marlenio, where we used the additive manufacturing technology to remanufacture spare parts. These were so-called pinions. They are used in an SEM Oikos X6-axis machine, used to cut wood to specific sizes that are required in the building of houses that way. And this specific pinion has a high wear. It's used in a high wear and tear environment. And it means that it's quite often needs to be replaced. Otherwise, the machine will be stationary and there's no production that way. The method we used for remanufacturing is first to recreate the CAD geometry. And we've done this via a combined method of analyzing existing parts as well as 3D scanning them, just to ensure that we have the correct geometry. And then the basis was to select a correct material, not only to remanufacture the part itself, but also if we are able to get increased performance out of it. As it's currently used in a high wear environment, if we can increase the wear resistance of the part, that also means that it has to replace less often. And for this, we used M300 tool steel on an Additive Industries Metal Fab 1 machine. That would give us the best properties of the material itself. So for this use cases, what we will manage to achieve is to get a very short lead time. If you would otherwise have to remanufacture these parts, you have to order material, you have to either set it up and make fixtures, etc., etc. In this case, all we needed was a CAD geometry, and within 1 or 2 weeks, we had the parts available. But also due to the choosing of an M300 tool steel, we managed to improve the wear resistance, and therefore also ensuring that this can be used longer inside the machine itself. The second use case I have in store for you is a use case we utilized at the Lucchini RS factory, where they are grinding train axles in a fully automated production line. And within the grinding process, one of the key aspects of that process is cooling your parts to ensure you get the correct surface finish, and also to ensure that you achieve the right tolerancing. You have to have a good cooling setup. Usually, if you are utilizing such machines, you have a general tooling or general cooling setup where you have to aim it at your part specific to how you want it, but you're still quite limited to the conventional setup. So for this site, we're choosing to use additive manufacturing to upgrade the existing setup. And with that process, we first defined the actual use case. How are we going to do it? Do we want to have multiple nozzles or one, or even, or can we combine it, or how can we best cool the application in this case? After which we created a couple of functional models out of ASI 316L stainless steel. In this picture on the right side, you can see the latest versions. In the slides of Mustafa earlier in this workshop, you could see the early versions, because we have validated and tested a lot of different versions, in order to improve it to achieve the performance we wanted. So with this upgrade of these cooling nozzles, the machining performance is increased. It's able to run faster with the same results. That specifically helps at fully automated production lines. And with this, we can achieve part-specific cooling applications. So these were my slides, and I want to give the floor back to Diego to round it all off.
Thank you very much, Rob, for the explanation of these use cases. As before, we have a couple of minutes for receiving any questions. So if anyone has a question about the former presentations of the use cases, please feel free to open your mic and ask the question to the speakers. But if not, I just want to give many thanks to the speakers. Has done very interesting presentations, and I think we have understood a bit more the depth of the work being developed in the Level Up project. So that's very interesting. And just give a big thanks to all the assistants to this workshop. If you want to know more about the Level Up project, there is the link to visit the website of the project, levelupproject.eu. And if you want to know a bit more about the Digital Factory Alliance, you can visit us in the digitalfactoryalliance.eu. Okay. If you have more questions after the webinar is end, you can address this question by email, and we will be more than happy to reply to any of your doubts. Okay. So for no more, thank you very much to the speakers, and thank you very much for the participants, and have a nice day. Bye.
Thank you too, Diego.
Thank you.
Bye, everyone.
Thank you. Bye-bye.
Thank you so much. Bye-bye.
Goodbye.
Have a nice day.